Hi, good morning. Today we will be going over the length of a curve. It's really not that bad. I hope you enjoy. All right, so there is a formula, and I'm going to give it to you now. And then right after that, we're just going to derive it, show the steps of how it comes about, really just give an explanation as to why the formula is what it is. All right, so arc length, or just length of a curve in general, sometimes referred to as arc length, is going to be the integral of a to b, where a and b are just your start and end points, your xi's, of course, of the square root of 1 plus f prime of x squared dx. Okay, so this right here is the formula, and I'm going to show really where it comes from. All right, it's actually all based on the distance formula. Just a quick reminder, the distance formula between any 2 points, we'll just say x1 comma y1 and x2 comma y2 is going to be your square root of x2 minus x1 squared plus y2 minus y1 squared. Another way that this is written is going to be your change in x squared plus your change in y squared. Okay, we could go more in depth on this. I'm actually going to do another video on just where this comes from if you're interested, but for now we're moving on. All right, so this right here is the distance between any 2 points. Okay, so if we're looking at an actual curve, let's just say this is our curve right here, and we want to look at the length of the entire thing. If this was just a string, I just put it in that little design. If I stretch it out, how much string do I got? All right, what's the length of my curve? All right, so this is going to be adding up a whole bunch of little distances. For example, let's just say I have these 2 points right here. You see those? Them in a different color. Let's go purple. All right, so we got point there, point there. All right, well, if I could just say that this was just a line, because if I zoom in close enough, it's going to look sort of just like a straight little line. Very short, but straight little line. If I could just say this is a straight little line, then I could say, okay, how long is that line? And then do it again. Do it again for these two at that line, and you'll see that I'm just adding a whole bunch of little sections. Well, when we're adding a whole bunch of little sections, that turns into an integral. So we're actually going to see where this comes from. All right, so I'm going to zoom in a little bit. I'm going to say, okay, well, if this was my whole curve, or whatever it was, you saw what it looked like. I'm going to say, okay, let's just look at this section. So I just zoomed in really, really closely. Let's just say, here are my 2 points from earlier, 1 and 2. I'm going to call this length here the change in x. So let's just say that this is your change in x. And this here, I'm going to call change in y. Okay, because we know the distance formula, which is actually based on the Pythagorean theorem, we know that this distance will be the square root of change in x squared plus your change in y squared. Okay, all right, so here's what we got. And since we're taking an integral, we want to look at when their x distance is as small as possible, when it's infinitesimally small. All right, so here's what's going to happen. We're going to rewrite this expression a little bit. We have our change in x squared plus your change in y squared. And since our x distance is infinitesimally small, we're going to call that, instead of change in x, we're going to call that a dx, a tiny incremental change in x. And well, since x is so small, that means our change in y is also got to be small. Because if I'm going over just a tiny bit, I can only go up so much, right? So that dy, that delta y is going to change into our dy. So I'm just going to make those necessary changes. I'm going to say, okay, instead of delta x squared, it's now going to be dx squared plus dy squared. And that right there is our length of that tiny little section. All right, and because we want to take all of these lengths, we want to add them all together, we will be taking an integral. But unfortunately, this, as it is not in the position to be integrated. I can't just take the integral of dx's and dy's. I have to have some type of a function in there, and I have to have some type of, with respect to, I have to have a dx or a dy at the end. So we have to change this a little bit. The way that this is going to work is I'm actually going to factor out a dx squared. All right, so let's check this out. We have a square root right there, square root of, I'm going to factor out a dx squared. Okay, well, what's that leave? That's going to leave just 1 here, right? That's just 1. Plus dy over dx squared. We still have that dy squared divided by dx squared gives us that. All right, well, this is kind of interesting because dx squared inside of a square root, I could take it out. I could just call that dx, right? Because square root of dx squared is just going to be dx, right? We know this. Okay, and that leaves 1 plus dy dx squared plus that. Well, dy dx, that right there is the derivative. That right there is your instantaneous slope at a single point. So I could just call that f prime of x squared. And that's exactly what I'm going to do. This right here, this right here is something we can take the integral of. We can just say, okay, integrate square root of 1 plus f prime of x squared dx. I have an integrand. I have something I'm taking the integral of. And I have my dx. I have all of the necessary parts of an integral. And if you'll recall, we're going from, well, I'll just give it bounds just for completion. Let's say we're going, oh shit, I'm going the wrong way. Let's say we're going from, I don't know, let's say we're going from A to B, right? This right here is the interval of which we want to get the length. So that would mean that we're just going to integrate this expression, this from A to B. And there you have it. That's going to be the length of a curve.